Here's a 2D kinematics problem to try. You're standing at the top of a cliff. You throw a ball with initial velocity v0 at an angle theta below the horizontal. So it's going to be going in the downward direction when you let go of it. And we want to know how far away from the cliff, capital D here, does the ball land, given some height of the cliff. And we are also going to find the time it takes that the ball is in the air. So we're given the height of the cliff, 50 meters, initial velocity 20 meters per second, and theta is 15 degrees. So you probably want to stop the video and try to set this up yourself. So the first thing you should always do is define your origin. And the second thing, define the positive directions. I've done that in red. I've also filled in with blue the x and y components of the initial velocity. And then the third thing I always do after defining the origin and the positive directions is filling in this little chart. Position, velocity, initial and final, acceleration and time. These 5 parameters that define the motion. In this case, it's a two-dimensional problem, so I'm going to split up the motion into x and y variables. All right, x, where does it start out? It starts out at x equals 0. And where does it end up? Well, that's what we're trying to figure out, isn't it? The initial velocity in the x direction, it is going in the positive x direction, and it's going to be v0 cosine theta, which is 19.3 meters per second. The final velocity and the initial velocity are the same, as is the velocity at any point in between, because the acceleration is 0 in the x direction. And time we do not know. Okay, so I've told you before that if you have any 3 of these 5 variables, you can solve for the other 2. That wasn't quite correct, because if one of those 3 things is 0 acceleration, then that doesn't really help us in solving for the other 2. So if the acceleration is 0, the 3 parameters isn't enough to solve for the other 2. So we need something else here. We don't have enough information to solve for x final. But if we knew the time, we could solve for x final. So let's look at the y motion. Maybe there's enough information there to get the time, and then we can plug that into the x and solve. So y, we start out at h, which is positive 50 meters. Y final is going to be 0. That's the split second before it hits the ground. In the y direction, what's our initial velocity? Well, it's going down, and it's going to be v0 sine theta. The final velocity we don't know, and you know what? We don't really care. The acceleration in the y direction is down 9.8 meters per second squared, and the time we do not know, but that we do care about. So the fourth thing we do is we choose an equation that's missing the variable we don't care about, in this case Vy final, and then we solve for time. The equation I would use is this one. It's y final is y initial plus v initial t plus 1/2 at squared. There's no v final in that equation. I plug in everything I know, and I'm very careful to keep the signs with the numerical values as I go. So negative 9.8, negative 5.17 for my acceleration and for my initial velocity. And I end up with a quadratic equation. So I have 2 roots for time, a positive root and a negative root. And negative time doesn't mean anything to us physically, so I'll throw that one out, and I'll set my time equal to 2.71 seconds. And I can use that now for my x direction. here's our equation. X final is x initial plus v initial t plus 1/2 at squared. Acceleration in the x is 0, and our initial x value is 0. So we get x final is v initial times t. And that should look familiar to you because a lot of us remember distance equals rate times time. Well, that's what we're getting here. Because our initial position was 0, x final actually is the distance traveled, and that ends up being just the velocity times the time, 52.3 meters.